Well, let's see another example of hydrolysis. Hydrolysis, in this case, of a salt that comes from a strong acid and then a weak base. Remember, this is the concept of hydrolysis. The concept of hydrolysis is the reaction from ions that come from a salt with water itself. You know that water is amphoteric and therefore those ions can react with it. Well, what acid as an example or what salt as an example am I going to give you? A salt from a strong acid and a weak base? Well, I'm going to give you ammonium chloride. The chloride, ammonium chloride, as you well know, is NH4. Cl is a salt that when we put it in water in aqueous solution, it will be completely dissociated. Let's put here dissociated. So I am indicating this dissociation, this complete dissociation with an arrow to the right. What ions can we see in ammonium chloride? On one side, the positive ion will be the ammonium ion. Ammonium, no, what else will there be? In solution to something, and since it's neutral, we should look at the other ion, which will be the chloride. Let's put it as Cl as well. In aqueous solution, to start with, a salt should give a pH of 7, unless either of these two ions Alright, what can we see? We have chloride here. Where does the chloride come from? This chloride, Cl minus, where does it come from? It comes from the complete dissociation of hydrochloric acid, HCl. This hydrochloric acid is an acid, as you well know, and it is a very strong acid. If it is a very strong acid, it means that when it reacts with water, liquid water loses a proton, gives it to the base, water acts as the base. And this water will cause protons to be present in it. The chloride remains. Sure, but why did I put this arrow pointing right for you? So because to the left, to the right is not going to happen. It's going to happen to the left. I've already said it to the right. Because it is a very strong acid, the chloride, which is the conjugate base, is an extremely weak base. And it's not going to cause the formation of hydrochloric acid, but rather it will be hydrochloric acid that will react with water, dissociate into its ions, and we will have only the chloride. Therefore, the chloride coming from a strong acid, as I mentioned in a previous video, this chloride it undergoes hydrolysis. So can we be at ease with this chloride coming from a strong acid? Yes. If I had a weak base, a strong base, it would be the same case, but it turns out I have a weak base. And what is the weak base? Well, here I am going to see it because I have the ammonium left. If I take the ammonium NH4+, in aqueous solution, this would be the acid, because it will lose the proton. The acid against whom? Against the water, against liquid water, and now it would form, and I'm going to put a double arrow. If this is the acid, it loses the protons. Let's do it. The water takes it away, and I would be left with the ammonia base NH3. This is the base. Of course, losing the proton and passing it to the water, that proton is lost. It stays bonded to water, which is what we call H3O+, hydronium ion. Sure, because of this ammonia reacting with water, here I have a balance. Here I have a balance. Therefore, I will have the presence of protons in aqueous solution, and therefore I'll have a pH lower than 7, which is an acidic pH. How much acid? What amount of pH less than 7 do I have? About how the equilibrium constant is shifted to the right. how to calculate this equilibrium constant. This equilibrium constant, given that is a hydrolysis reaction, then to this equilibrium constant, I'm going to call it K sub H, or hydrolysis constant. Like any equilibrium, we already know how to put it. It's K sub H, or hydrolysis constant. We're going to put it, how we will put in the numerator, what we have in the products. As it is written, the ammonia on the top. NH3, which is the base. Weak is the ammonia. I will also have the concentration of protons, H3O+. And at the bottom, the concentration of ammonium ions. You know that the concentration of pure water is constant. And therefore, it is already directly included in the hydrolysis constant. Okay, how to calculate this constant? What data will I have? I will have the basicity constant of this base of the doll. And the elasticity constant of ammonia, I'll stand here. Ammonia that reacts with water to determine that constant which they will give to me. I'll put the reaction balance of the base with water. On the other side, to the right, the ammonium ions, NH4 plus and hydroxide OH in solution. Aqueous. That is the equilibrium of the reaction of the base with water. This equilibrium is called the basicity constant, as you well know. This basicity constant, in reality, let's see that it doesn't fall. This elasticity constant, K sub B, is actually in here. I'm going to put it, and you'll see it's in here. I'm going to put it, but it will turn out a bit different for me. Like any constant, at the top I have to put the products, the ammonium concentration. Ammonium, the concentration of hydroxides. And what do I put on the bottom? Not water. I put ammonia, NH3. This is the basicity constant, which is data from the problem. They will always give me the basicity constant, and with this, I will calculate the hydrolysis constant. If we compare this here with this over here, it's similar, but not the same. What can I do? What do I have here? Notice it's backwards. Therefore, if I do the inverse of the acidity constants, I will have the concentration of ammonia on top, down below the concentration of ammonium, the concentration of hydroxides, and whether it's complete here or not. Because I have protons here, and here I have hydroxides. How can I remove this? Easy. If I multiply at the top and bottom, because of the concentration of hydroxides, OH, how much am I multiplying by? I'm multiplying by 1. Combine the concentration of protons with the concentration of hydroxides. And this would be the ionic product of water, labeled Kw, which is 10 to the power of negative 14. I know these values. And what's left at the bottom? At the bottom, notice what I have left. Ammonia, ammonium, and hydroxides, which is what I have here. And this over here is the same thing I have up here. Then here, this would be the inverse of K sub B, and therefore I'm going to put it at the bottom. Once I have the hydrolysis constant, what do I do with the hydrolysis constant? Should I erase up here? Because what I want is to calculate the pH, and we agreed that I will get an acidic pH, but I need to calculate it. How do I calculate that pH with the hydrolysis constant? Alright, I've already calculated the hydrolysis constant as the quotient between the ionic product of water and the base constant K sub A, whose data I will have, but the hydrolysis constant will be the concentration of ammonia, the concentration of protons divided by the concentration of ammonium ions, NH4+. That's what I have here. Here, I have the hydrolysis equilibrium that allows me to get the constant. If I know the hydrolysis constant and balance it, from there I get the proton concentration, and once the proton concentration is obtained, it's straightforward to get the pH, which will definitely be less than 7. So, to summarize, hydrolysis reaction of the ions that come from a salt with water if possible. In the case that these ions come from a strong acid and a weak base, notice that the one who is going to beat me will be the strong acid, and therefore I will end up with an acid pH lower than 7. Alright, this is the theory, but let's move on to the practice. So now we'll gradually tackle problems. Come on, let's get to it.